Okay, here we go. Good afternoon, everyone. Welcome to lecture 2 of ECE 231. I recently heard someone on the faculty refer to this as the ECE course because this is a class that really obviously is combining elements of both the EE curriculum, that is the circuits and the interfacing and the hardware part, and the computer systems curriculum, which is the computational aspects, the programming and the just the thinking about the computational part of an embedded system. So this really is ECE. It's combining both of those elements together. So you should see my PowerPoint slides up on the screen right now. And I'll just let me tell you what we're going to do today. I think that today should be a somewhat shorter, somewhat lighter day. Things will start to get a little heavier once we get into it on Wednesday. What I'm going to do is kind of give you an overview of the C programming language today. Just sort of a, what the heck is C useful for? Why does it exist, and what is it? And then we'll start to get into the code on Wednesday. My aim is not in the course to teach you C programming, really. It's to learn enough of the C language so that we can do our business, which is programming embedded microcontroller chips. So we have to learn some of C in order to do that. But the reason why I say my aim is not to teach you C, much of C programming is used for creating operating systems, creating big programs like Word, or creating compilers, and involves using the terminal, that is the keyboard, monitors, things that really are beyond the scope of an embedded system. So in this course, we'll be using C in a certain way, and so all of the complexity of C we won't need to be concerned with, but enough of it so that we can find our way through to program these chips to make them do our bidding for us. So let me just give you some announcements. First of all, homework number 1 is posted. It's posted to this week's tab of the Moodle course. It's due in 2 weeks, so you sort of have plenty of time to work on it. But I urge you not to wait because, like all these problems, if you wait until toward the end, particularly if you wait till it's due on a Sunday at a minute before midnight, you'll find there's less help available to you in the weekend. During the week, we'll have people in the lab staffed with hours. And in fact, the schedule for our TA support in the lab in Marston 221 is now posted to the top of the Moodle site. You can go there and you can see who's going to be there when, and you can go there for help. And we tend to have relatively little coverage on the weekends, and so that's why I say you want to get going on this assignment now. Don't wait till 11 days from now to start it. In order to do this assignment, you have to install Visual Studio Code, and you have to install a compiler, what's called a tool chain, on your machine, and set up your programming environment. And whether you're using Windows or Mac OS, there are 2 documents that I posted last week. They'll tell you in detail how to set up your environment. So do that now so that you have the tools ready. And if you have difficulty, you can consult with one of the TAs using the schedule that's posted. We're still getting ourselves organized with the TAs. Some of them will be offering Zoom hours, and I need to get those Zoom links to you. We may also be setting up a Piazza site as a way for you to post questions, and we could answer those online. So I'm still working that out. You're going to get a kit in the class to do your work with circuits and embedded microcontrollers. I'll give you more information about that on Wednesday. For the first 2 weeks, you don't need a kit. Everything we're doing on the first 2 weeks is just sitting at your laptop. Okay, let's get into it. So first of all, C, you may have already sort of know that C is what we think of as a medium level language. We talk about a high level language, we talk about low level language, and I wanted to just say a little bit about that. So you've already, most of you have already learned Python. before. Python is an example of a high-level language. Java is another example of a high-level language. Assembly language we think of as a low-level language, and C is sort of in between. It's a medium-level language. So what's this all about? Well, let me get a pen going here. And there are different definitions, but for our purposes, when we talk about a high-level language, think about the things that you've done in Python. It's easily understandable to you, human-readable instructions, and the details about the machine are abstracted away, so that when you wrote code in Python, you didn't care about the memory locations. You didn't care about what the actual machine looked like. That is the microprocessor. Whether you wrote your Python in a Mac environment or on a Windows environment, I mean, in both cases, the microprocessor involved, whether it's a Mac or a Windows machine or even a Linux box, they're using the same machine language. It's the x86 machine understandable language. But you didn't care about any of that when you were doing your stuff with Python. And the code that you wrote was interpreted. That is, every time there was an instruction that was executed, a high-level operation took place to take that line of code, interpret it, translate it into the machine understandable code that the actual microprocessor understood. And all that happened, and you weren't even aware of it, right? And so as a result of that, code runs kind of slowly. You don't have access to all the hardware guts of the machine, but you're perfectly fine for a lot of the things you wanted to do. If you get down to the bottom, the lowest level, then you're talking about the processor itself, whether it's the processor inside your laptop or the processor in one of these embedded chips that we're going to be working with. Those things only know ones and zeros. The processors only know how to execute binary code bit patterns that are the machine code language associated with the architecture of the microprocessor itself. And so when we write code in C, in this sort of medium language, we'll have access to the memory and other machine level features. So it's not all hidden away from you the way it is when you're doing something at higher level. And the code that we write, instead of being interpreted, you're going to write the program in C, and then we're going to compile it, take the entire code and translate it down into the machine code so that it can be understandable by the operating system. Was there a question there? Okay.
I did not see a question.
Okay, fair enough. So, so just a little bit about C history and its use. I mean, it's not crucial that you know this, but I just wanted you to have some perspective on it. So first of all, it was written by Dennis Ritchie at Bell Labs in the late 1960s. So you were not born yet. So the late 60s, early 1970s, and they wrote it as a language that they could use to write the Unix operating system. And there's a classic reference called the C Programming Language by Kernighan and Ritchie that came out in 1978, right? Just something for you to know about. FYI, the predecessor language to C was called B, right? I don't know if there was an A before that. When it was first written, it was not yet standardized, or there were different conventions by different people who used C. In 1989, standardization took over. So you have ANSI, the American National Standards Institute, and ISO, International Organization for Standardization. ANSI and ISO, they said, let's standardize this. Let's create a language that everyone understands and that meets a standard. That's what we're using here in the class. We'll refer to it as ANSI C or ISO C. It goes back to this standard written in 89 or 90. Now, since then, there have been modifications to it. You may see reference to this. So C language from 89, 90, 99, 11 is 2011. You don't have to worry about any of that. The point is, for our class, we're just going to be using ANSI C, which is standard C. If there's ever a time when it's important for us to know the difference between what we're doing and standard C, we'll call that out. Okay, you've heard of C++, no doubt. It's kind of an extension or a superset of C. It's a different language. It has a lot of things that are common associated with C. We won't be doing C++ here. We'll be using C. Okay, what's written in C? What else? Well, a lot of big systems code. So operating systems, for example, parts of Windows, parts of Mac OS, Linux, iOS, parts of all those are written in C. Interpreted languages like Python and Ruby, those are written in C. For our purpose, embedded processor control applications are written in C, and that's what we're doing. Okay, some features of C. So this is how people often will describe the C language. You need not sort of memorize any of this. I just want you to sort of hear it so you kind of have access to it. So you've seen it before. Okay, so access to memory locations. And this is sort of a big important thing for us. We won't be programming in assembly language, so we're not going really low, but we'll have to have some awareness of memory locations and registers inside microcontrollers, and C provides that to us. And as I said before, that kind of stuff is hidden or abstracted away if you work with Java or Python. Like a lot of software, C code is portable. It can run on different machines. That is, code that you write to run on one processor, like the Atmega 328P processor that we'll be using, that code can also be written to run on a completely different processor. Now, how is it that that works? How does the same code, which has an understanding of the the memory locations, how does that work on different processors? Well, you have to take pains and write the code the right way so that it can be compiled to different target machines and actually run on different processors. And so you have to be kind of deliberate in doing that. But C can be portable. It's also efficient, and by that we mean it has relatively few keywords. It's a small set of actual reserved keywords in the language, and I'll show you what they look like. The code that we'll write is going to be small, relatively small programs that'll run fast. Okay. C is written to enable you to write modular code, which, it's sort of the divide and conquer approach that you've heard about in software. We won't be writing really huge programs, but when you write big programs, what you want to tend to do is break it up into small pieces, and each small piece gets a job done, and it's encapsulated in such a way that you need not concern yourself with the details of how a piece of code is implementing, but rather what is the code doing rather than how it's doing it. We call that encapsulating. There's an external library, an important external library associated with C, and we'll be learning about that. There's something called a macro preprocessor, which we'll learn about. And then I just wanted to show you a couple of useful quotes about C. So the first one, C never doubts the programmer. So in a lot of languages, like if you were doing something in Python, it would help you out in the sense, if you made a mistake, it's going to tell you and it's going to prevent you from getting into trouble. In C, if you've done something, if you've written something really crazy in your code that can really mess up things elsewhere in the system, elsewhere in memory, for example, the language assumes you know what you're doing, and it assumes that you are being deliberate. And so the language can cause you to really screw up as a result of that. So it's written in a way that it never doubts the programmer. So if you insist on coding something a certain way, the compiler can give you a lot of warnings, but if you choose to ignore the warnings, it's quite possible to really screw up using C. That last point, I think you'll start to see, I think you'll resonate with this. C, it's quirky, it's flawed, and it's an enormous success. Okay, so how are we going to create a C program here? Well, first you're going to create a file of C code in the text editor, and you're going to save it with an extension .c. All right, and I want to go through and show you this. It may be that some or most or all of you have sort of seen a lot of this already, in which case we can speed it up. But after you write the source code, you're going to compile it, and you're going to use what we call the GNU GNU C compiler. At least initially we'll be using the GNU C compiler. Then that's when you're programming on your laptop, making use of your keyboard and monitor. Then when we switch over and start programming for microcontrollers, we're going to use what's called the AVR GCC. AVR is the processor inside the microcontrollers we're using. GCC again is the GNU C compiler. These are both open source compilers. You get them for free. By now, I hope you have installed the first compiler on your system. If not, it's time to get going with that. The next step, though, after you've done both of those things, well, once you try to compile code, you'll inevitably see a bunch of compiler errors, warnings that are just warning you you're potentially doing something wrong with your code, or actually errors that prevent you from compiling. You fix those errors, and then you either run the resulting binary executable file, right? We call it a binary file. It's a bit pattern of ones and zeros that your microprocessor on your machine understands, right? You don't understand it, doesn't make sense to you, but it makes sense to the microprocessor. So that's if you've written code and you've compiled it directly onto the processor on your laptop, say. Or if what you're doing, and we'll get to this in 2 weeks, if you're writing code that you want to exist on a target microcontroller, the next step would be we call it flashing. You flash the resulting binary executable file to the flash ROM that exists on the target microcontroller, and then it'll start running. So that's the process, and I'll walk you through this. Let me just tell you a little bit about programming environments. Okay, so first I want to talk about IDEs. These tend to be big. An integrated software development environment is a combination of an editor and a compiler and a debugger and lots of other things, all sort of built into one package. They tend to occupy tens or several tens, up to 50 gigabytes of disk space, depending on all the bells and whistles you add. Examples, some of you may already be experienced with using Visual Studio, for example. That's the Microsoft product. It'll run both on Windows and Mac OS. And by the way, last class, someone asked a question about Linux. My presumption is that most of you are using Windows machines, and a smaller but not insignificant fraction of you are using Mac machines. And I'm not aware of anyone using Linux machines. If you are using Linux, do let me know. Otherwise, I'll sort of always be including Mac and Windows in my examples. In any case, Visual Studio runs on all those platforms. That's the Microsoft product. If you're writing code for Macs or for iOS, for iPads, for Apple Watches, for iPhones, you would use Xcode. There's also Eclipse, which is another one of these IDEs. But these are big integrated development environments, and they tend to have a fairly steep learning curve associated with them. We're not going to be using one of these environments. If you're doing professional coding and you're going to spend a long time to get up over the learning curve, you would invest the time to learn one of these. We're going to do something else. In addition to those kinds of environments, which exist for writing sort of software, all kinds of apps on all kinds of platforms, there are also integrated development environments specifically for embedded programming. And the microcontrollers we're going to use, the Atmega 328P chip, which is the brain inside of an Arduino Uno. It's called the AVR processor. That's currently manufactured by Microchip. They also have a family of processors called the PIC microcontroller. Both of those families of processors are supported by two different IDEs from Microchip. There's Microchip Studio and then MPLAB-X. And these are larger IDEs. They take about 10 gigabytes of space, and they have significant learning curves associated with them. Last year, when I taught this course, we did the course using both of these, using Microchip Studio and MPLAB-X. But I think that many of the students really spent way too much time just trying to learn the tool and sort of suffering from not understanding the software tool itself. So I'm going in a different direction this year. By the way, another IDE, another integrated development environment is the Arduino IDE. And that exists primarily originally created for artists and hobbyists. People are now using it for rapid prototyping. You'll be using an Arduino Uno board in the class, the actual piece of hardware, but you won't be using the Arduino IDE in this class. It's because programming involving the Arduino IDE, for the most part, is not done in standard C. It's done in an Arduino, sort of a lighter weight Arduino scripting language. And it's sort of all the things that we care about with low level or medium level C programming are, a lot of that is abstracted away in the Arduino scripting language. So we'll be using the hardware, but not the IDE. Okay, what are we going to be doing? I've chosen a lighter weight option. When I say lighter weight, it takes up less space on your hard drive, and there's just sort of overall effort involved in getting up to speed and using it and managing it. So we're going to be using a text editor. We're going to be using the command line, which would mean the terminal app on your Mac or the command prompt app on your Windows machine. Those are called command line. And we'll be using a compiler, a tool chain that you download. So it'll take you less time to get up to speed using these things, so we can spend our time instead learning to code and learning to code microcontrollers. Okay, so more specifically, the editor that we're going to be using is Visual Studio Code. Now, I've come to understand that many of you, in fact, most, maybe all of you, already have familiarity with Visual Studio Code from Python. And what I'm going to do is this. What the heck have I? What I want to do is I want to see if I can. I could do a poll here, but instead, I think what I would just like to do instead is I want to blow you up so I can see you on my camera or on my screen. And would you do me a favor? And if you're familiar with Visual Studio Code from a previous class, would you just put your hand up in the air and wave it back and forth? Okay, all right. So that's most everybody. Thank you. It's sort of what I expected. All right. So Visual Studio Code is really just a text editor, but it has a lot of nice features when you add the C++ extension. It'll help you create your syntax. It'll color code the syntax. It does things called code folding, and it'll help us to develop C code. If you opt not to use Visual Studio Code, there are other editors you can use. There's BBEdit for Mac. There's Notepad++, and there are others. Some of these are free. Some of them cost money. Some of them have they're free for a certain amount of time. If you use those, that's okay, but you're sort of on your own there. Whereas the teaching team will support you and be able to give you detailed help if you're using Visual Studio Code. So that's how we're doing this. Okay, the command line interface, it will be the terminal and command prompt. I'll show you. I'll give demos of those. Okay, and then the compilers that we'll be using. For just 2 weeks, we're going to be using a compiler that makes use of your console, your keyboard and monitor, and then we'll switch over to a different compiler altogether. So we're going to go through a kind of a fair bit of work to download and set up an environment with these two compilers for using your console, that is for writing code on your laptop. And it's actually a fair bit of work, and it'll take up disk space just for 2 weeks. And then we'll be done with that, and you can remove those from your disk, and we'll be switching over to use a compiler specifically for coding the embedded microcontrollers. And so why are we doing this? I think it's easier for you to learn C if we spend 2 weeks doing some console applications where you have a keyboard and you have a monitor available, and it's very straightforward to do I/O and write your code and test it using keyboard and monitor. Because once we get to using a microcontroller chip, that's headless. There's no monitor unless we take pains to put one there, and there's no keyboard unless we take pains to put one there. So that's this is sort of the game plan here. A couple weeks learning C using your console, and then we'll go headless. Okay, how much disk space is all this going to take? It's going to take about 2.5 gigabytes of disk space, which it ought not to be a big problem for you. But I am aware from previous courses that for some of you you can be close to the end, to the edge of your disk's capacity. So I just wanted you to sort of see this. So to start out, this is where we are for 2 weeks. Then after the first couple of weeks, you can get rid of the console stuff and get a couple gigabytes back, and we'll just be using Visual Studio Code. So for now, I want you to be thinking about Visual Studio Code and the CLang compiler if you're a Mac user, or the MinGW64. That stands for Minimal GNU Windows Compiler 64-bit. But anyway, that's all described in fairly great detail in a couple of notes that I've posted to last week's Moodle tab. So follow those, put these compilers on your machines, and then you'll be able to get going. Okay. So actually, I just discussed this. Our learning approach for the semester, 2 to 3 weeks. It's really going to be 2 weeks. 2 weeks. Learning C on a general purpose computer, where you've got the console there, and then for the rest of the class, I'm dividing it up into 2 pieces. It's all going to be embedded C coding. First, we'll be using the Arduino Uno development board, right? Wave your hand if you've used an Arduino before. Okay, so you've probably done that using the Arduino IDE, unless you actually have done embedded coding before, which is unlikely. But we're going to be making use of the Arduino Uno board because it's easier to. What we want to do is program the chip, and the Arduino Uno board has a lot of things to provision the chip. It has a built-in power supply, a voltage regulator. It has a clock. It has various interfaces that'll make it easier for us. So we'll spend 5 to 6 weeks on that. Then we'll put aside the Arduino Uno board, get the bare chips themselves, the $2.50 chips, put them on breadboards and program them. But to make those work, we're going to have to put voltage regulators and crystal oscillators and other things on them. So that's the game plan here. Okay. Okay. Set up your environment. I'm repeating myself. Make sure you download and install Visual Studio Code if you haven't already. Download your tool chain, and then you want to start to get to know the command line interface if you haven't already. If you haven't worked with the terminal app or the command prompt, then you want to start to get to know that, because that's how we'll be using it a lot. This next slide is just a list of instructions, typically used command line instructions on the left. And then I have 2 columns, one if you're using Windows and the other one if you're using Mac OS. I won't speak to any of this now, but I wanted you to have it as a reference for when you start to do some work with the command line. Okay, how are you going to build a program? Well, first of all, I want you to get used to the language of project. So every time you start a program, I want you to think about it as a project. And so when you create a project on your computer, create an entire folder or subdirectory. They'll mean the same thing for that project. And the reason why is each project is going to have multiple files associated with it. There will be your source code that you write. Then there may be, and sometimes you may find that your source code occupies multiple files. And then as you compile it, you'll actually get the binary executable file to go along with it. And soon we're going to start to use what's called a makefile, which is a way of automating the compilation process. So the point is, there's a handful of different files that's associated with every project. So you want to make a directory for the project. Okay. And so the way you're going to build a program, you're going to create a directory, you're going to navigate to the project folder, you're going to launch Visual Studio Code, you're going to enter the source code, and then you're going to compile it, and you're going to run it. And I'll go through the steps. I'm going to show you a 13-minute demo of that in just a minute. And then once you've successfully compiled it and you now have a binary executable code that is understandable by the microprocessor in your laptop, you're going to run it. If you're running it in Mac OS, this is how you do it. You're going to type // and then the name of the executable. And if you're on Windows, you'll just type the name of the executable. Okay, so I'm going to just show you Hello World. Hello World by a convention. The very first program that you make when you start to learn any language is just one that just prints Hello World to the screen. Thought question for you, by the way. So if we accept that you're learning a new language, the very first thing you want to do is just get it to print hello world to the screen. Because if you can do that, it means you've got the environment set up, you've got your editor, you've got your compiler, your tool, all these things called the tool chain, the path, all that kind of stuff is set up right, and you can successfully get the words hello world printed to the screen. Hooray. How do you do that? Or what does it mean on an embedded controller that has no screen? How do you do hello world? That's, I won't answer the question now, but that's just something to put out there for you. Okay, so this is when I stop talking and I show you a 13-minute video of me creating hello world, first on Mac and then on Windows. And I hope you're able to, from the back of the room, see the fonts here, but you'll let me know if you can't. Okay, so let's go ahead and create our first very simple program. First, I'll do it on Mac, and then I'll do it on Windows. So to start out, I'm going to open up Terminal, and I'm assuming that you've already been successful in setting your path variable. Let me just increase the font here a little bit. So the very first thing we're going to do, you'll notice that this has opened up in my home directory. And if I were to type pwd print working directory, you'd see that I'm in users/Dave McLaughlin. That's called my home directory. Okay, and let's just, some of you have had difficulty setting the path. So let me just show you what the path should look like. That's what that should look like. And we'll cover that in a separate memo. But let's go ahead, I'll clear this screen. And what I'm going to do is I'm going to make a folder or a directory. I'll use those terms synonymously. I'll make one called coding projects, and then I'll make a subfolder for the project hello world. So make your coding projects. And so this can kind of be the parent folder or the parent directory that we'll put all of our various coding projects in. And each time we start to create a new file, a new program, we'll create a separate project folder for that. And that's because each file has associated with it a number of, or I should say each program has associated with it a number of different files. There's the source code file. Sometimes there will be multiple source code files for one program. And then there are various other files that get generated along the way as a result of compiling. So we'll talk about that in more detail later on. But for now, just go with the idea of making a dedicated project folder. So I'm going to move into coding projects. I'll make the folder for hello world. Make your hello world. Okay, I'll move into that. Now I'm going to open up Visual Studio Code. So if you've been able to successfully set the path variable to also include Visual Studio Code, then we can launch that from here. And so that is opened up. So the very first thing I'll do is I'll create a source code file. I want to call that hello main. Let's see. And we'll go ahead and type that. I'm going to first just put in I'll put in kind of a nothing comment, just so that we have a comment. So I just want to stop there and find out whether you can see this at all, or am I just wasting your time having you look at this because the font is so small? If you're unable to see the font, would you just raise your hand? Okay. All right. I figured that would be the case. So, so rather than have you sit through 13 minutes of something that you can't see at all, I'm just going to skip it. And it's this little video is embedded in the lecture notes, so you can go and see it, and you can just sort of see me going through and creating this code, in real time. I'm going to have to figure out the best way of projecting things so that the font is big enough for you to see, given that we have a couple windows that we need to have you see, but we'll figure it out. Okay, so I'm gonna ask you to look at that little video for how to make Hello World on your own after class, and I'm gonna let you out early so that you can do it. Okay. All right. Let's just take a quick look at the structure of a C program. So you'll have the same issue with not being able to see this code here, but I just want to make a point here that, first of all, what I hope you're able to see is that you have a bunch of different colors there. You have green on top, and then you have, some blue and some brown. Visual Studio Code is smart enough to provide all those colors for you, and that'll help you to create code. It'll help you to debug it. It'll help you to sort of format everything. So this is a program that we're going to be looking at in sort of more detail later on. All I want to do here is call out some pieces of it. So at the very top of the code, there's a block comment. And the block comment, it just tells you what the program does. And you'll see in every example, I tend to put quite a bit of time into building a block comment. Otherwise, a couple weeks later, I have no idea what the code does or when I last revised it. All right, you can do block comments or single line comments. Next, we have a bunch of things that are called preprocessor directives. They begin with the pound sign. So way over here, which I'm going to assume you can't see until I figure out how to get them big enough for you. But all these lines begin with a hash, the hash sign or the pound sign. Those are not C commands. Those are called preprocessor directives. And what they do is they tell the compiler to do some kind of a macro replacement before it actually goes ahead and compiles. And so if I take this line here, it says define days in year 365. What that means is everywhere else in the code after this, when the compiler encounters days in year, it replaces that with the number 365. Okay, so that's a symbolic constant. We'll talk about why you do that. Okay, the next thing in here, we have something called variable declarations. All right, there are a bunch of variables that are being used in the code. I have year of birth, age in years, age in days, age in hours. Let me just tell you what this code is doing. It's asking the user to type in their year of birth, and then the code just tells them, okay, at your next birthday, this is how many years you'll be. This is how many days you've been alive. This is how many hours you will have been alive. And it also goes on to say, based on your age, you're a baby boomer or you're a millennial or you're a Gen Z or something like that. So it's just sort of some simple outputs based on how, a user's entered age. But there are a number of variables that are being used in the code. And so here we have a bunch of what are called variable declarations. Okay, everything that you see in here is called the main function definition. And so the code starts, there's this line, int main void, and then there's an open brace. For now, just memorize that or write it down so you have it, you'll have it available to you. You'll write int main void and then brace hundreds of times through this class. So you'll see what the purpose of it is. So what I'm showing you here on this line is so far there's a block comment, there are some single line comments, some things called a preprocessor directive, and then our code itself is packaged into what's called a main function definition. Then we have variable declarations. Over here, I have some input and output from the keyboard. And those are actually function calls. I'm making use of a function called printf. That's for formatted print to the screen. And there's also scanf. That's for formatted input. Printf and scanf are called function calls. Okay, I have some assignment statements. So I have a statement down here. Age in years is equal to current year minus year of birth. That's an assignment statement. I have a variable called age in years, and I'm assigning that a value. And I'm computing that value with the stuff on the right side of the equal sign. And I'm just talking about this at high level. We're gonna see all this in more detail later on. Down here toward the bottom, I have an if-else control block. You will have seen if-else and blocks previously. The syntax is a little different. Where you put the commas and the braces and the semicolons is a little different. But what this is just an if-else control block. All right. This over here is another version of the same code, and I'm going to just flip back between the two. Actually, you can't see it, so I won't even bother flipping back. The only difference is down at the bottom here, I've just changed the way I put the curly braces. We have what's called inline curly braces versus in-column curly braces. And that's strictly a formatting thing. It's a way of writing code that is pretty or easier to see versus more difficult to see. Given the size of this font and the fact that you can't see any of it from a few rows back, I'm not going to elaborate on that right now. Here I want to show you the same version of the code. But what I've done is I've hidden away a lot of the commands in functions. So I think at this point, what I want to do is, David, what's your view? If I have something like this, how far back can people read it?
I would guess probably not very far back, in 4 or 5 rows. Maybe
Okay.
possible.
Okay.
I can barely read it from the front.
Okay.
So my eyesight's not that good.
Yeah. Okay. All right. So a fair bit of the slides that I have for you, you won't see. That's okay. I want to show you just in terms of right now, the basic structure of a C program, so that if you look at a program, you say, okay, I recognize that that's a C program. The basic building block is a function. And so C is really a collection of functions. The first function, it looks like this. It's called main. Every C program has to have a function called main. And so it's going to have a structure like this. It has something called a function header. For now, just think int main void is just something that you have to do because of the syntax. Just like, you know, when we use written English, right? Written language, if it's English, you know, we agree that you're going to capitalize the first word of a sentence. You're going to capitalize a proper noun. You're going to use a comma or a semicolon in certain places. You're going to indent paragraphs. This is all the syntax of English. Well, likewise, every programming language has its own syntax, and I'm just showing you some of the syntax and structure of C. So for our purposes right now, when you're writing a C program, you're going to have this. Most of the action is going to take place in this function called main. You'll start it out with this header, int main, and then the word void in parentheses. And then you'll have some curly braces. Curly brace here, and then a curly brace here. And these will define the body of the main function. And then you'll just have a whole bunch of C statements, as many as you need. So that's the first function that you'd have in a C program. And then you may have some other things that happen before the function, block comments, some things called preprocessor directives, some things called function declarations. And then you may have some additional user-defined functions that follow. They'll look like main, but they'll have different names. So here I have a function called A, right? And you would give it the name A, or you give it any name you want. And then I have a curly brace, a bunch of statements, and then I have a closing curly brace. And then down here, I may have a function B, you know, and I've just chosen to call them A and B. So this is a program that's comprised of 3 functions. It's main, and then it's function A and function B. I just want you to appreciate that the functions are the building blocks of a C program right now. Okay. Just a little bit more detail about a function, and this is sort of what I just described on the previous slide. If you have a function, okay, one function, what we want to do as a good programming practice is put a block comment before the function that states, it states what the function does. It doesn't have to describe how it does it, but it states this is what this function does. And so you can see I have a slash, a forward slash, and a star. And then I have my block comment. And then I end that with a star and a slash. That's a comment. That's just there for you and me and the other humans that might look at the code. The compiler ignores it. So C doesn't learn about it. The machine, the microprocessor never learns about or cares about this. This is a block comment that's there just to tell any human that's looking at it, this is what this function does. Okay. Okay, then we get into the structure of the function itself, which I just went over on the previous slide. What I wanted to show you here, and you can't see it, so I won't even try to talk you through it because you can't see it. But I will see if I can get you to see this. These are just two different versions of the same program. What the program does is not important, but what I've done in the one down below is I've taken out all the white space and the comments. So I've taken all of the actual instructions, the preprocessor directives, the function definition, the curly braces and everything, and I've just packed them all together without space in between. It's virtually impossible for you to look at it and understand what the code is doing, but the compiler doesn't care. As far as the compiler is concerned, both of these are exactly the same program. And the question is, which one would you rather work with, right? If you had to debug it, or if you had to inherit it, like if I gave it to you and I said, here, work with this, right? Or if you were going to share it with someone else, which of these two would you rather work with? Well, you would much rather work with the top one because you have some hope of figuring out what that code is doing, because there are ample comments. It's a lot of white space. I've separated things out. So you can look at it and say, okay, I have a sense of what this code is doing. I can make sense of it. Whereas the one on the bottom where there's no white space is impenetrable. You can't figure it out. And so here's another example of that same thing. And maybe you can see this. This is the code that I wrote in that little 13-minute video that we sort of aborted. And this is just a program that all it does is it prints hello world onto the screen. Okay, up at the very top, I have my block comment, right? It begins with a /* and it ends with /*. This is how I tend to write a comment. I've got the name of the file, and then I have a comment. This program prints hello world to the display monitor. It's written for a laptop with a console rather than a headless embedded microcontroller. Compile using GCC, not AVR GCC. Whether that makes sense to you or not is not important, but I wrote it as a comment to myself. Also, when I write code, I keep track of a revision history. More on that later on. Okay, then we get into it. This is the actual structure itself. I have it's called an include statement. I have my int main void, and I've defined my main function. It's just got one line. It prints hello world. And then there's a statement called return, which ends the function. On the next slide, I'm going to show you the same thing, but I'm going to take out the comments and I'm going to take out all the white space. Here it is here. So which would you rather I show you? I mean, of course, you'd rather I show you code that has a big enough font that you can actually see it, right? But when you're working with code, C allows you to really pack a lot of things together, put everything on one line, and do it all without white space. But and you can save a lot of space when you do it. But without white space or with comments and white space, the question is, which one would you rather have? C allows you to do this, but we're not going to do it in the course. So in the course, we're going to make liberal use of what we call white space and comments. I just have to figure out how to enable you to see all that on the screen. Okay. Let's see. This is going to end up being quite a bit abbreviated class because a number of the slides I was unable to show you. But I want to just, I'm going to end this class today with this one line, or this one slide, and it's just some things I want you to know. We'll talk about all these points in detail beginning on Wednesday. First of all C programs must have a main function. Okay, at the beginning of C programs, you'll see these things called preprocessor directives. They begin with the pound sign, or what people call the hash symbol. Those are not C statements. They're commands for the compiler before it actually compiles the code. If you're going to have a variable in your code, you have to declare it. So anytime you have something in the code, whether it's a variable or a function or something called a structure, you have to declare it before you use it. There are 5 types of statements in C. There are function calls, there's assignment, there's a declaration, a control, and a null. None of this may make sense to you right now, but it will as we go along. This next point, coding without writing comments is cruel. It's allowed in C, but it's not allowed in this class. So make sure you use comments. Okay, the rest of this, I'm going to pick it up on Wednesday. So I'm going to let you go there. You do have these slides, so take a look at them particularly in the 25 minutes that I'm giving you back in your schedule. Okay? I'll stay on if you have any questions up front or
Professor,
yeah.
after we've dealt with any questions, we can do some experiments with what text is readable, what text is not.
Yep, that's a good
There's
idea.
a few tools in the room